Welcome to Spring Lib.
So, um, once again, welcome to a new problem. We're dealing with acoustics. Remember, if you think about acoustics, this is the science of sound, and in this instant, we do have diffraction going on, and we also have interference going on. Remember, interference is when wavelengths collide on each other. So we have interference and diffraction, which is like bending of light. So in this particular problem, assume we have a slit, two openings actually on the slit, and there's speakers on the opposite side of the slit, and obviously there's sound that's going to be spreading. There's going to be sound spreading. Maybe we have to backtrack that a little bit. Have the speakers right here. And if you think of these speakers, they're obviously producing sound in variable time. So there's sound going in variable times, like that. We do have speakers in between. So right here, we have speakers that are helping us simplify this particular problem. So if you have a speaker right there, and then the sound is going to come out and expand and spread, and it's still moving as waves in the right direction. The same thing is going to happen on this other opening. So there's spreading of sound. So think about when you drop like a stone inside of water, and the stone begins to spread out. The water begins to spread out in waves. So this is what's happening in this particular problem. And obviously, you're seeing there are specific connections in the problem, and we have a variable delay line, right here. So this is variable delay line, and there's signaling on the opposite side, and we have it's an audio signal. It's an audio signal generator. It's an audio signal generator. So this is what happens in this particular problem. So it's a double slit. So think of it as a double slit. That's one thing that's happening, and the gap right here, this gap between these two openings is D. The openings themselves have a width of A. That's the opening themselves, and so there are two loudspeakers that are producing the sound, and you can see there's a variable delay right there. So phase, think about phase as an angle of displacement, between waves. Or for example, this wave right here can have a phase 1, and then this wave has a phase 2. So that's the angle that they're moving, and so there's a gap between them in terms of the phase angles. And so one of these speakers, we can kind of adjust the phase. You can adjust the phase so it's variable. Variable is something that's changing. So what we're looking at is that if you adjust, so this is our question, if you adjust the difference, or if you adjust the gap, between the phase angle of the speakers ranging from 0 to pi, or rather 2 pi. So it's like, speaker one has phase 1, and then speaker 2, we have 2 speakers in openings, has phase 2, and so between them there's a gap from 0 to 2 pi in terms of phase angles. If you want to think of it in waves, you have one wave and then you have the other wave coming in. So what we're saying is that this gap right here, we want to vary it from 0 to 2 pi. That's the gap we're looking at. And assume we have interference going on and also diffraction. So interference is kind of like the collision of waves, and then diffraction is kind of like bending when the waves go through an opening. So we want to see our goal in this particular problem is we want to see what happens as we drift away from the openings. So this distance you drift away from the openings is that, what happens over time? What's the pattern over time in terms of interference and in terms of diffraction? So that's what we're looking for in this particular problem, more of like a conceptual problem, but we do have an understanding of specific things that happen. So we're saying if phase 1, which is the first opening, minus phase 2 equals to pi radians, then there's going to be a reverse of theta r equals to 1.22 lambda all over d. Remember, lambda is the wavelength. You want to think of lambda as the wavelength. The acoustics are followed, whereby the bright fringes become louder, and that's the main thing you're looking at. And then the dark fringes become silent. The dark fringes become silent. So that's one thing we're looking at. And then we're also going to add on and say for a phase difference of 180 degrees, the peaks. So, I mean, when we talk about the peaks, this is a sine wave, and these are the peaks. So the peaks of the sine waves. So the peaks become valleys. So these peaks right here are going to become the valleys. These are valleys. These are valleys right here. And these are peaks. The peaks are going to become the valleys. And the valleys become the peaks. So that's what's happening in this particular problem. And then the changes, we'll say the changes in phases. The changes in phases happen from 0 to 180 degrees and 182 through 60 degrees. So those are the changes happening, and the shifts in peaks are non-stop. They're non-stop, so it's a continuous process. And at the middle of diffraction, we're going to have a dip gap at the center. Okay, so that's what we're saying. And then we're also going to summarize by saying the central maxima disintegrates into a much smaller maxima with locations at specific angles, and you know, these angles are going to be at modeled with a sine theta equals to plus minus lambda. So once again, you know, we had a problem, and as you can see, there were two openings, two slits. The slits were distance d apart. Each width was a, and the speakers produced the sound, which is moving in the right direction, and they pass through the openings. There's going to be phase differences between these two waves. So this is phase 1 and this is phase 2, if you want to call it that, and we can have some variation in the phase angles. So there is a delay right there, so this can produce variation in the angles. This is the audio signal, and it's a double slit experiment, and so there's a displacement between the waves, as you can see. So our goal in this problem is to explain really what happens on the other side as the light goes through. And so there's a delay to produce different phases of one speaker compared to the other one. So we're doing that. And so we want to see in this double slit diffraction, you can see there's diffraction. So interference will be taking place, and also diffraction will be taking place. So those are two things we're looking at. And that happens because these waves are gonna, interfere with each other, collide, and there's also gonna be out of phase with each other. So our goal is to explain, what happens over time as they move through towards the right. So if we adjust the gap between the angles, so the phase angles we adjusted from 0 to 2 pi. As you can see, these are the gaps can be as small as 0, so they overlap, or close to 0, or even all the way up until 2 pi. So we have interference. So if phase 1 and phase 2 have a difference of pi radians, then there's going to be a reverse of theta r with that relationship. And so we do have some acoustics going on right here. There's bright fringes and dark fringes. The bright fringes become louder and the dark ones become silent. And then also, if there's a phase difference of 180, what happens is the peaks, these peaks right here, become valleys, and these valleys right here become peaks. And so that's what we're seeing, and happens from 0 to 180, and then from 180 to 360. The shifts in peaks happen non-stop. So, it's a continuous process. So this one goes to a valley, and then the valley goes back to a peak, and then the peak goes back to a valley. So it's a continuous process. And so the central maxima splits into smaller maxima, which are modeled by this equation. So hope you enjoyed the problem. Feel free to send any questions or comments, and have a wonderful day.